So I'm going to talk about learning to reason for robot task and motion planning problems. So I think in the past few decades, we have made a great progress in terms of low-level control and motion planning for robotics, where the robot has to reason about low-level details, such as geometry, physics, and kinematics, in order to change the internal state of the robot. So now we have a way to control a complex humanoid to jump onto a box, plan its footsteps in an environment with a complicated geometry, and have a Kai's Hubo to open a door in a rather unstructured environment. So building on this advancement, the problem that I'm interested in is something called the task and motion planning problem, where we have to reason about from a high-level objective, such as packing boxes on a moving day, cooking a meal, or constructing buildings, down to such low-level details in order to change not only the state of the robot, but also the state of the environment. And in order to do this, we need to define an interface between the task-level planning and the motion-level planning. And we call this interface an operator, right? An operator is basically a computer program that consists of three things. One is the input parameters. Second thing is a model. And the last thing is the output, which is basically robot motion. So here is an example of a pick operator. Its input consists of three things: which object to pick, which robot base pose to use, and which grasp to use in order to pick up the object. So let's say the robot decided to pick up this particular object using this particular robot base pose and using this particular grasp. What happens inside the operator is that it checks by calling an external motion planner, checks if there exists a collision-free path from where it stands now to the chosen base pose. And it also calls the external IK solver, the kinematic solver, to check if there exists the joint angles to pick the object with the given grasp. And if all these are satisfied, it tells the high-level planner that we can pick up the object, and it outputs the motion that picks up the object. And using this formalism, a planning algorithm for task and motion planning problem basically takes in two things, initial state and a goal state, and it outputs a sequence of actions that will get you from an initial state to the goal state. And each of these actions are basically operator instance, where the operator instance is basically an operator type plus its specified parameters. So for example, for the pick operator, we had to define object O, base pose, and a grasp, and that completely specifies an instance of an operator. And associated with each of these operator instances is a sequence of robot configurations that actually achieves the robot motion. So this sequence of configurations might be a pick motion for picking up the object. And inside the planner, we've got three things: a search module, a sampler, and a feasibility checker. Search module is basically a graph search algorithm, so such as you can think of it as A star, depth first search, and so on. But unlike the traditional graph search, we have a sampler to deal with continuous variables, such as the base poses, right? So what we do at the search time is that we're going to choose the next node to expand according to the search algorithm, and then the sampler will sample the promising values for these continuous variables. Then what's going to happen is that the sampler will call the feasibility checker, such as a motion planner, that checks if these input parameters that we sampled are actually feasible. And if these feasibilities are checked, then we can simulate forward from the node that we are in to the next node, and then the search control goes over to the search module, which then selects the next node to expand. And basically, this process of expanding a node and selecting the next node to expand repeats itself until we arrive at a particular go node. And there have been many different work in the past few years in terms of how do you come up with a better search algorithm by designing a better heuristic, or how do you come up with an intelligent sampler that will generate good enough samples that will always get you to the goal state. The trouble with these methods is that they're typically slow and they do not improve with experience. And primary reason that they're slow is because they have this complex hybrid search space. So let's say we are trying to cook a meal for dinner, right? The robot needs to decide on the discrete decision variables, such as which object to manipulate in order to prepare the meal. And as you can imagine, as the number of objects grow and the planning horizons grow, it'll run into a combinatorial explosion. We also have to decide on the continuous decision variables, such as where should the robot stand in order to pick a particular object. And this needs to satisfy certain physical and geometric constraints. And these are usually reasoned out by calling an external low-level motion planner, which usually is expensive. So in order to avoid this computational problem, we might use learning, right? So we can train a neural network that'll try to map a state to a low-level robot control that'll such that it'll maximize the sum of the rewards along a particular time horizon. The premise here is that there exists some kind of smoothness that the function approximator can exploit in terms of patterns with respect to the states and action spaces. The problem for task and motion planning problem is that even for a small change in state induces large change in the feasible motion. So for example, here the task of the robot is to place the object that it is holding inside the storage room, right? And this is a feasible motion for placing the object down for this particular planning problem. Now, if I move this blue object by 50 centimeters, then we need a completely different maneuver to place the object down. And this not only happens with respect to the changes in states, but also with respect to the changes in actions. So here, the robot is trying to place this object down. And if the policy that you trained missed this target by 0.05 meters, then it's going to collide with the obstacle, and you suddenly have an infeasible action. So based on this observation, we can see that a learning would require a lot of data because you need to learn all these details. On the other hand, if you can train such a policy, then almost no online computation will be required. Planning, on the other hand, is computationally difficult because we need to find a solution within this complex search space. But we don't need any data to train a planner. So now we can think about a spectrum between a complete learning and complete planning approach. A complete planning approach is difficult because we have this complex search space. Learning a complete solution, such as a policy, is difficult because we need a lot of data. So what I try to do in my research is to sort of sit in the middle and learn to guide planning by predicting constraints that guides the planning procedure. And by constraints, I mean a set of suggestions to a subset of decision variables. So the total number of decision variables for this particular problem instance might be all the configurations for placing this object down. But if we restrict ourselves to predicting the robot placement base pose, then that becomes much more smooth with respect to the changes in the state. And for the rest of the decision variables that have to exhibit the collision-free behavior, we're going to delegate it to a low-level motion planner to adapt to the changes in the environment. So our overall strategy, will be to leave out the variables that are difficult to learn and have the planner fill in the rest. So typically, a planning algorithm maps a problem instance to a solution, but this is really slow. So what we do is that we learn to predict constraints, and then the planner will now enjoy a smaller search space that satisfies these predicted constraints. So here's an overview of our approach. We're going to take in a past planning experience as our training data set, and then we're going to design a learning algorithm that's going to output a learned predictor, right? And this learned predictor will take in a problem instance that is represented with a particular vector representation, and then it's going to output a constraint for this particular problem instance. And then the planner will have to output a plan that satisfies this constraint. Now, this poses two challenges. One is how do you come up with a representation for these kinds of complex planning problems? And the second thing is how do you design a sample-efficient learning algorithm for learning from past planning experience data set that's a bit different from traditional supervised learning or reinforcement learning data set. So why is representation difficult? So one of the reasons is that we've got different relevant objects. So for example, let's say one day the robot faces a problem instance of picking this blue object that's lying on this desk. And what's relevant here are the objects that are lying on the table. The next day, the robot comes in, and it's faced with the same problem, but different instance. So now the blue object is in the shelf, and what's relevant are the objects within this shelf. And these objects that are lying on the desk are completely irrelevant. Another complicating factor is that we have this varying number of object shapes and varying number of objects and varying object shapes. So here, the robot is trying to pick up this black rod and then place it onto the desk on the other side of the room. And we've got a certain number of object shapes and object number. But next day it comes in, it faces a much bigger rod, right? And it has different number of obstacles that are lying on the desks. So these two factors, different relevant objects and varying number of objects and their shapes, forces us to ask these questions. Should I encode all the object shapes and poses into an input vector when only a subset of them are relevant? And how do I know which pose go into which dimension? So for example, if I decided to encode the pose of this computer, then does that go into the first dimension or second dimension, or does that not really matter? And it turns out the right representation for these kinds of problems is a set with varying cardinality rather than a vector. And current machine learning algorithms can't really deal with this kind of representation. Another complicating factor is that we have this logical and geometric object states. So going back to this problem of cooking a meal for dinner, we have symbolic object states that encodes whether the object has been cooked or not. And we also have a geometric object state, which encodes the x, y, z, and roll, pitch, yaw of the object. And all these factors really make it difficult to design a fixed size vector representation. And this is one of the challenges that I deal with in my research. Another challenge that I deal with in my research is the fact that we have a planning experience data set. So let's say we have, as our planning experience, solved a lot of instances of packing objects into this type bin that you typically face in a warehousing environment. Then what you get as a result of solving each of the problem instance is this search tree where one of the trajectories lead to a goal state, and the rest are sampled and checked. And for the rest of the actions that you've sampled and checked the feasibilities for, didn't really lead to anywhere, right? So this kind of data set, I call them a neutral data set. So we have one trajectory that actually led to a goal. So in a classification term, we might call them a positive samples. And we have these neutral set of trajectories that we don't know if they're positive or negative. So we might conclude that this state that we ended up in might be a dead-end state or a cycling state that we actually come back to. Or this might actually lead to a goal state if we expanded if we sampled more action and searched more enough. So, and the problem is that we have a number of neutral trajectories outnumber those of the successful trajectories vastly, right? So, natural question that we can ask is how can you leverage such neutral trajectories in order to come up with a more sample-efficient learning algorithm? And so I'm going to first discuss a work that I did in order to tackle the neutral data set problem in a geometric task and motion planning problem. And before I dive in, I just want to talk about what is geometric reasoning. So basically, geometric reasoning is reasoning about reachability among obstacles. So traditionally, roboticists have studied a lot about a point-based robot back in 70s and 80s, and trying to make that point-based robot to get to the goal state while avoiding obstacles. We had a breakthrough back in the 90s, and we have sampling-based algorithms that can plan a path for high degrees of freedom robot while avoiding obstacles. And now we've gotten so good at it, we can simultaneously balance the humanoid and get to the goal state while avoiding obstacles now. So based on this advancement, the geometric task and motion planning problem can be stated as follows. Given an arbitrary number of objects with varying shapes and poses, change the object poses to achieve a high-level objective. So here are a couple of examples. The robot is in some kind of warehousing environment, and it's receiving some boxes from a conveyor belt, right? And its job is to pack these objects into this relatively tight storage room. Another example is a robot might be on a moving day, and it's in a room full of boxes that are packed, right? And what it needs to do is that it wants to fetch a particular box, and it needs to figure out how to move all these boxes out of the way in order to reach this target. And all these really requires reasoning about how do you pick the object and how do you place the objects such that you can satisfy the collision-free constraints. So can you come up with a long sequence of collision-free motion that will achieve these high-level objectives? And in order to focus first on the neutral data set problem, I'm going to make some simplifying assumptions, which are that we have same object shapes and same number of objects. And these assumptions allow us to free from the representation problem, because we can now represent a problem instance with a vector. And just a reminder of how we search, as we said, we're gonna do random sampling plus graph search. So at every search node, we're gonna sample k number of actions, and then we're gonna search with a sampled actions. And as I said, as a training data set, we get this kinds of search tree. And one observation that we can make is that if we can sample promising actions that are likely to be on a goal trajectory, then the planning will be much more efficient. And if you take that argument to one extreme, if you can come up with a sampler that always gives out the action that will always lead to a goal state, then no search will be needed at all. So our objective is to learn a stochastic policy that generates promising actions using past search experience. So here is a problem formulation. So given a set of search trees that we got by solving n number of problem instances, where we denote the problem instance with omega, that are solved using a uniform random policy, Q, that conditions on the problem instance omega and a particular state, learn a policy that assigns high probability to the goal trajectory, which we're going to denote with P. Right? And one approach that we can take is to train a generative adversarial networks using successful trajectories. So we're going to take all these state action pairs that led to a goal state, and then we're going to show it to a GAN, and then train a generator that generates actions that are like on the solution trajectory. So here's a quick intro to GAN. What it basically does is that it learns a transformational random variable using a neural network. So basically, it takes in some random variable z that is sampled according to p of z, and after seeing a lot of values of x's from a particular training data set, g of theta, the neural network, transforms this random variable into another random variable x, and this implicitly defines the distribution pg of x. And a typical example of this is to generate images. So you might, for example, sample a z from a normal distribution, and then you're gonna feed a lot of images of dogs. Then G will learn to generate images of the dog such that it matches the distribution of the training data, which we denote with PD. And it does so by learning a discriminator function. So the discriminator function, what it does is that after seeing a value of x, it tells you whether the x is real, which means that it's coming from the distribution PD, or fake, which means that it's the one that is generated by the generator G. So if the G successfully generates an image of a dog that is realistic, then it says, oh, that's a real image of a dog. But if it fails to generate an image of a dog, then it's going to be able to tell that it's a fake, right? So if we apply this framework to our problem, then our stochastic policy is basically represented with this generator G. And we're going to train a discriminator as follows. We're going to take those actions that are sampled from P, which are basically, so that means we're going to take those actions that were on the solution trajectory, and then we're going to train a discriminator such that we increase the values for the values that were sampled from P, and then we're going to decrease the values for the actions that are generated by G. And then the generator, in turn, will try to tune its parameters such that it maximizes the values of D. And these are going to be trained in alternating fashion, and eventually, hopefully, that we can get a good enough G that generates promising actions. So this is all in great, and we can train a stochastic policy that generates promising actions. But the question that we had at the beginning was that, how can you use the much cheaper neutral trajectories, right? And then the challenge here is that the neutral trajectories are sampled according to a uniform distribution Q, whereas the successful trajectory actions are sampled according to P. So what we need to do in order to use these samples from distribution Q is that we need to change the GAN objective, right? And one thing we can do is that write this expectation with respect to Q rather than P, right? And one other observation that we can make is that the support of P is in the support of Q because Q defines a uniform distribution over the entire action space. So if we have this importance ratio, then we can multiply this WA by the inner term in this expectation, and then rewrite this expectation with respect to Q rather than P. Now the question, of course, is can you compute this importance ratio? It turns out that there has been an extensive set of work in machine learning literature in estimating this importance ratio using few samples that you have. And we take this particular approach that was devised back in 2009 by Kanamori that basically minimizes the least squares error with respect to the target importance ratio. And one change that we're going to make from their work is that we're going to use a neural network to approximate this W hat instead of linear architecture that they use in order to guarantee some theoretical performance. So if we do that, so if we estimate the importance ratio and change the GAN objective, then we arrive at GANDI, which is our algorithm. And the key difference between the GAN objective and ours is that we have written now the expectation with respect to Q because we've multiplied the inner term in the expectation with the importance ratio that we've estimated. And if we do this, we gain sample efficiency plus computational efficiency. So here the robot is in another warehousing environment type of task. It needs to stow some objects, 4 to 8 objects, into this relatively crowded bins by selecting its base pose and the object placement poses. And if you give it 20 seconds to a planner with the uniform random policy, then it solves about 17% of the problems. If we train GAN and have 35 training episodes, then it solves about 50% of the problems. And if we use GANDI, then we solve about 50% of the problems with just a 10 number of training episodes. So this is 3 times gain in the computational efficiency, as well as 2.5 times gain in the sample efficiency with respect to how much training data you have to give to each of these learning algorithms. And we have similar results in other tasks as well, which I'll be happy to go into detail offline. But we get similar results in terms of the computational and sample efficiency gains. We also have a theoretical result that relates the error in the importance weight estimation. So when we say that if the error in the importance weight estimation is bounded above by epsilon squared, then our KL divergence between the P, which is the target distribution that we wanted to learn, and the one that we learned, PG, is bounded above by this function right here. And I'll be happy to go into detail about the proof of this theorem offline as well. So those were for geometric tasks, and I tackled the problem of mutual data set problem. Now I'm going to move on to more generic tasks where I focus on the representation problem. So just to go back and motivate the representation problem, we had this problem where we had two different types of object states, such as the symbolic object state and geometric object state. And for the planner, this allows it to handle more a diverse set of problems, such as cooking a meal. But for a learning algorithm, it poses a challenge because it's got 2 different types of object states. So what we propose is a bit different, is quite different from what people have used in traditional machine learning literature. And what we want to do is that we want to propose the most general representation with the fewest assumptions. And this particular representation is something called a score space representation, where we basically represent a problem instance with the scores of constraints. So for example, if you have a space of problems, then each problem instance has a corresponding score space representation, where the x-axis of this function is basically constraints, and y-axis is basically the scores of these constraints. And these scores are basically representing the quality of the plans that satisfy the constraints. So you can think about a length of a plan for when you have to use a particular robot base pose or grasp. And the intuition here is that all that matters to a predictor that predicts a constraint is how the environment responds to its prediction, not how the environment looks like or how the robot looks like even, right? And if you have this kind of representation, then we can formulate the constraint prediction problem as an optimization problem, where our goal is to find the optimal constraint that optimizes this particular score function that represents this particular problem instance. The problem is that this objective function is unknown, and it is expensive to evaluate, because evaluating each constraint means that we have to solve for a plan that satisfies that constraint. So we changed the objective, we changed the problem a little bit, and what we want to do is now find the optimal constraint by optimizing an expensive to evaluate black box function. And typical approach that people do in machine learning literature is a Bayesian optimization approach, where we assume that this black box function f that you want to optimize is a sample from a Gaussian process. And what we do is that we choose the next point to evaluate according to some criteria, and there were many different approaches proposed for this particular problem. But one particular approach is a GPU-CB that basically tries to maximize the upper confidence bound of the current belief of the objective function. And if we do this, so this red here is the target function that we want to optimize. The blue is the mean value that our estimate of mean value for this particular function. And the gray area is basically representing the uncertainty about this function. And all these are flat at the moment because we have no information about this target function, right? But as soon as we evaluate a particular point, right, then our uncertainty shrinks down at this particular point as well as the nearby points. And if you repeat this process by maximizing this particular criteria, then we get to we can see that we can be more efficient in terms of number of function evaluations by explicitly modeling this uncertainty in the objective function. The trouble with applying these kinds of Bayesian optimization frameworks to our problem is that typically a covariance function that measures a similarity is required for these kinds of Bayesian optimization problems. So for example, going back to this toy example, we've evaluated a particular point here, right? What we need as an input to the Bayesian optimization algorithm is this kernel function that measures a similarity between the evaluated point and the unevaluated point. Right? And based on the similarity function, we reduce the uncertainty. The problem is that it is non-trivial to design such a covariance function over the space of constraints because of the problem that I mentioned previously, where we have a large change in rewards with respect to the changes in the space of constraints or actions. So what we propose is a different kinds of Bayesian optimization algorithm, which we call black box function optimization from experience, where it does not require such a hand-designed similarity. What we do is that we first discretize, we solve a lot of training problem instances. So we solve n number of problem instances, and we extract from these problem instances particular values of the constraints that the solution for this omega-1 satisfies. So let's say we extracted particular grasp, base pose, and placement pose as a solution for this planning problem instance. And what we do with these extracted values is that we evaluate them according to with respect to the other problem instances. And if we do this, what we get is a matrix of scores where each row now approximately represents the score space representation of each problem instance, right? And what we can do with this matrix of scores is that we can estimate the prior distribution over the belief of the target function. So from this, we can compute this mu hat and sigma hat by looking at the values, by summing up the values and dividing them by n, and so on. And so offline, we are going to do all these work by solving n number of problem instances and getting this score matrix, and then evaluating this parameters for the prior distribution. And then we're going to feed it to a Bayesian optimization algorithm during the online stage. And what the Bayesian optimization does is that it goes on to that typical belief update and suggesting value type of strategy, where it selects the next action, next constraint to evaluate based on that GPU-CB criteria. The planner then evaluates that constraints by coming up with a solution that satisfies that constraint for this new problem instance omega n plus 1, and this loop sort of repeats until we get a satisfactory plan. And if you apply this framework to problems that have a varying number of objects and shapes, we get about, so this is our algorithm box, and this is a static algorithm, which is another score space representation algorithm. and this is a raw planner, we get about 6 or 7 times gain in the planning problem efficiency, planning efficiency. And for this particular problem of choosing base poses and grasp for picking this blue object that could be on any one of these 4 tables, we get about 6 times or 4 times gain in the planning efficiency. And we also get similar results in this lost particular problem as well. And we also have a theoretical result on our algorithm. Basically, what we do is that we analyze a simple regret. And regret basically is a comparison between the actual optimum and the optimum that we've evaluated so up to time t. Right? And the result is that our algorithm is no regret, which means that as the number of evaluations grow, our regret goes to 0 eventually. And that's it for my talk, and thanks for listening. 질문 있으시면.
저는 이 분야가 아니긴 한데
네.
주로 하신 건 연구 분야는 플래닝 타임을 줄이거나 아니면 시도 횟수를 줄이는데 그런 퍼포먼스를 얘기한 쪽으로 하죠.
네, 그러니까 이 문제들이 보시면은 서치 스페이스 자체가 컴플렉스하기 때문에 그냥 플래너를 돌린다고 하면은 정말 몇십 분이 걸릴 수도 있는 문제들이거든요. 근데 그런 문제들을 러닝을 통해서 거기다 힌트를 준다고 보시면 되는 거예요. 그 힌트를 줌으로 인해서 그 서치 타임이 훨씬 더 줄어들게 되는 거죠.
지금 주로 시뮬레이터로 하시는 거죠?
네네.
하드웨어를 해보신 적이?
하드웨어로 이제 다음 스텝입니다. 그거는. 네.
그러면
네.
해보실 때 지금 부족한 게 뭔가요? 지금 연구하시는 이런 연구를 하시는 입장에서
네.
뭐 주변이 그러니까 뭐 시뮬레이터건 뭐든 준비가 원하시는 만큼 안 돼 있을 것 같은데 어떤 쪽이 준비가 되면 내가 더 좋은 연구를 할 수 있다 뭐 이런.
그게 그러니까 하드웨어적인 거 말씀하시는 거예요? 아니면
다요.
일단 하드웨어가 있으면 좋고요. 예를 들면 그 PR2로 제가 주로 시뮬레이터를 돌려서 실험을 했는데 PR2 같은 경우에는 이제 물건을 잡아 올리거나 하는 것도 되게 문제가 있어요. 이런 박스를 잡아둘 때도 이게 힘을 얼마나 줘야 될지도 모르겠고, 그래서 그런 프리사이즈한 포스 컨트롤이 가능하면 좋고요. 그리고 또 이제 이게 사실 여기 시뮬레이터에서는 안 나오지만 uncertainty가 있어요. 내가 object를 뭐 이렇게 잡는다고 했을 때 사실 내 팔이 여기 있기 때문에 물건이 제대로 안 보이는 경우가 생기거든요. 그럼 그런 경우는 uncertainty를 어떻게 reduce 할 수 있을지, 그걸 센서에다 달아야 되는 건지, 그런 것도 이제 필요하고요. 만약에 그런 거 하드웨어적으로 풀 수 있으면 좋겠죠. 네, 그리고 이제 또 다른 거는 그 피직스에 대한 건데요. 이 물체가 어떤 프릭션 코에피션트를 갖고 있고, 이제 그거에 따라서 내가 가야 되는 힘이 달라지니까요. 이제 그런 거에 대한 언노운도 있기 때문에 그런 문제들이 아직 있습니다. 그래서 이제 그런 거를 에스티메이트 할 수 있는 거를 그런 알고리즘이나 아니면 하드웨어적인 해결 방법이 있다면 좋겠죠.
연구할 때 컴퓨팅 파워가 문제가 많대요.
아니요, 컴퓨팅 파워는 문제가 안 돼요. 이 문제들이 결국에 그 P-스페이스 컴플리트한 문제들이기 때문에, 그러니까 아무리 이제 내가 지금 GPU를 던지거나 CPU를 던져도 이게 오래 걸리는 문제들이기 때문에 이게 단순히 CPU 문제는 아니에요.
첫 번째 발표하신 부분에서 리프레젠테이션 키처가 어떻게 되는지 정확히 키지 못합니다.
네. 그러니까 거기서는요, 제가 이제 어썸션을 만들었어요. 그러니까 심플리파잉 어썸션을 만들어서 이제 모든 object들이 쉐입이 같고, 그리고 포즈가 이제 주어지고, 그리고 object의 숫자가 같고, 그러다 보면 이제 각각 이제 그 object 자체를 그냥 벡터에 넣을 수 있는 거죠. 그 object의 포즈 자체를.
사이즈 벡터.
네, 픽스 사이즈 벡터로 이제 뭐 5개의 object가 있다 그러면은 5개의 포즈로 되는 거죠. 그러니까 X, Y, Z, 로, 피치, R로. 네.
제가 그 초반에
네.
그 리프레젠테이션 만드는 것도 이제 상황에 따라서 베리어블 사이즈 문제가 있나요?
네네.
어제 그런 거죠, 제가.
그러니까 이게 그래서 이제 제가 두 번째로 고안하는 방법이 이제 스콜 스페이스 레프레젠테이션이라는 건데요. 이게 기존에 이렇게 내가 막 이렇게 비전을 통해서 뭐 environment를 나타낸다거나 하면은 이게 할 수가 없는 거예요. 제가 아무리 생각을 해봐도. 그래서 이제 사실은 근데 내가 어떻게 세상에 보여지든 그게 상관이 없고, 사실 로봇한테 중요한 거는 내가 어떤 액션을 취해봤을 때 그거에 대한 피드백이 더 중요한 거거든요. 그래서 내가 컨스트레인트들에 대해서 그 피드백을 내가 어떻게 prior information을 갖고 있을 수 있으면 이제 그거에 대해서 좀 더 확실하게 프레딕션을 할 수가 있는 거죠. 그래서 아까 보신 이 매트릭스가 결국에는 이 하나의 로우가 이 problem instance에 대한 approximation이 되는 거예요. square space representation의 approximation이 되는 거예요. 이 n개에 대한 constraint에 대해서만 이것들의 스코어들을 갖고 있고, 그리고 이 전체적인 스코어들을 갖고서 내가 이제 이 prior distribution을 내가 estimate를 할 수가 있고, 그럼 이제 내가 새로운 문제가 주어졌을 때 이 파라미터들을 갖고서 내 스콜 스페이스 레프레젠테이션은 이럴 것이다 라고 이제 내가 에스티메이트를 좀 더 efficient하게 할 수 있는 거죠. 네. 그래서 여기는 오브젝트가 몇 개 있건 아니면 오브젝트의 쉐입들이 어떻게 돼 있건 상관이 없어요. 우리가 전부 이제 신경 쓰는 건 이 스코어들일 뿐이에요.